Wastewater sewage is basically water with some relatively soft, solid material in suspension. Well, solids handling size has been the classic standard for evaluating sewage pumps. Fibrous and stringy matter are often a more concern, particularly as combined sewers are phased out. Combined sewers have drainage stormwater, which tends to dilute soft material, but also introduces more hard stuff. Non-clog impellers are at best clog resistant, and in spite of what people claim, you can clog anything. Typically, the classic pump has a minimum number 1 to 3 deep veins to handle spherical solids. And as a sloppy rule of thumb, residential pumps should be able to handle 40 to 50 millimeter, in other words, 2-inch solids. Subdivision pumps serving a subdivision up to about maybe 3-inch solids would be ideal, and main trunk ones 4-inch and higher. The leading edge of each vein in the pump is rounded to prevent stringy material from catching. Full diameter closed impeller shrouds can be utilized, in other words, a full diameter top and bottom, possibly with vac vanes, even though you may trim the vanes, have the shroud full size. This is something Metro Vancouver has done. Take a lathe and actually cut inside, but leave the full shroud top and bottom so material can't curve around the edge and get back to the shafting. Now, you can also get wastewater pumps which have a semi-open impeller and slanted leading edges along with a cover plate with some sort of machine groove or spiral in it. To be honest, the first approach is Flight Xylem. The second one, I think it's ABS does it with a multifaceted swirl to it. The effect we have is that creates a semi-grinder type of pump, better able to handle fibrous material, but more costly to repair. With a minimum number of deep veins, non-clog pumps are simply not able to handle low flow rates. This plus or minus 50% BEP really is important with sewage pumps. And because of the cut water and the vibration set up by the pressure vane going past, operating at the extremes, either extremely high or more commonly extremely low flows, can lead to clogging because the flow path isn't decent, noise, as I mentioned, close to the cut, and all that vibration because the impeller is so deep, you can start busting shafts because of the loads that are involved. Now, one of the things that you run into talking about wastewater pumps is self-primers. Now, they can be used in applications where the pump is located above the liquid source, maybe maximum 15 feet. Self-priming pumps do have non-clog impellers, but otherwise have features in common with conventional self-priming pumps. The casing has large inlet and discharge chambers. They're fat. The cut water is very close to the impeller. There is an internal recirculation port so that fluid from the discharge side can go back into the inlet, and there is an air vent to vent off the air that goes through the pump and discharges. First, the pump casing has to be filled with water or sewage before you can play the game at all. When the pump is started, a mixture of water and air is drawn into the impeller, vortexing. We talked about vortexing. This is doing it deliberately to get that air drawn into the pump. The close cut water directs this mixture into the discharge chamber, and the air will bubble out of the water and is vented off, okay? The recirculation port at the bottom allows water to keep refilling the inlet side of the beast. And I say air is vented off until all inlet air from the pipe has been removed. They will, you see the water level, the pipe that's split there, water level, sewage level is down low, and there's air in it, but it will, by, as I say, creating a vortex, sucking it into the pump, splitting the air off, letting the air go up and liquid go down, and the liquid go back into the casing to keep the process going. They will actually eventually bring that liquid up inside, through a check valve until everything's done. The check valve is there basically so when you stop it, it doesn't all back drain. The design features necessary for a pump to be self-priming also result in some rather undesirable characteristics. The need for the cutwater to be very close to the impeller means that impellers cannot be trimmed unless the cutwater can be repositioned. That is rare. Hydromatic did it at one time with their pumps. They actually had a backing plate with different sizes, lengths of cutwater, so you should trim the impeller you put in a larger cutwater. Self-priming pumps very often are belt driven so that they can adjust the pump speed to get the desired impeller tip velocity without having to trim. Having the cutwater very close to the impeller results in a noisy pump, particularly if only a two-vane impeller, which is typical of sewage wastewater pumps. Jamming between the impeller and the cutwater, therefore, is a distinct possibility and does occur. The internal casing recirculation port results in low pump efficiency. It's just going around and around. Need to vent air to atmosphere can be difficult to accomplish. Sometimes you just simply let it waste air and whatever, just in other words, a vent line, that's it. You can have fancy little devices that very often don't work. Another thing, of course, maximum suction lift capability is actually improved at higher rotating speeds. But like all pumps, suction lift is limited to a value below atmospheric. And even a small pinhole suction leak will result in an inability to pump. And there again is another drawing of the thing showing how it's priming, and you can see the air coming in. The water vortexes, it draws air into the pump. The water separates out, the air goes out, and we keep doing that until we hit liquid. Once we hit liquid, liquid goes in and through the impeller and discharges, except the recycle port keeps circulating some, which is basically lost energy. Essentially all wastewater pumps are end suction with cantilever impellers and volute type diffusers. The need to bigger non-clogged pumps having minimum number of deep impeller vanes to handle large spherical solid mean they have a limited flow rate. Again, you can't afford to go beyond the plus or minus 50%. That is a safe rule to follow. In operating at the extremes of performance could lead to clogging, noise, shaft break. We've been through that before, but it's worth repeating. Often mounted vertical casing venting will depend upon discharge pipe venting provisions. Fortunately, recessed impeller and grinder pumps are able to handle the smaller applications, because if you've got a sewage pump that can handle a significant solid size, by definition, you just have created a high capacity pump. So recessed impeller and grinders allow you to play games. They have no minimum flow range limitation, and recessed impeller pumps are both smooth and quiet. Now, let's take a look at recessed. Vortex, or recessed impeller, basically have a multi-vane impeller set back. If you look at this cutaway, you can see it's behind the basic casing itself. And what it does, it creates a fluid motion that provides a centrifugal pumping effect. In other words, the impeller really is just creating a vortex, and that's what's actually doing the pumping. They're not very efficient, but they do offer several advantages. They're very good at handling fibrous and stringy material. And yes, you get fibrous and stringy material, particularly in domestic sewage, and we won't take that any further. Generally, a 50 millimeter solids handling vortex pumps will match the solids handling performance of a 75 millimeter or 3-inch solids handling pump. Vortex pumps can operate anywhere in their performance curve, provided there's sufficient power when operating at high capacity. The horsepower required curve just kind of keeps climbing. So the higher the flow rate through the pump, the higher the horsepower needed. The multi-vane impellers swell away from the cutwater, so these pumps are quiet and smooth. They do run very well. Grinder pumps, basically what they are designed to do is first convert any solid material to a fine slurry, then have a relatively low capacity, high head water pump type impeller take over and actually do the pumping. It is the lack of large solid matter that permits the utilization of a narrow multi-vane, semi-open or vortex impeller. They're intended for low capacity, high head applications. and should be considered only when no other type of sewage pump is suitable. That sounds nasty, but that's one of the things I would say. The last thing you should be looking at is a grinder pump. As motor torque is required for grinding and shredding the solids, pumps with three-phase motors will perform dramatically better than those with single-phase. If you have a single-phase power supply, I honestly would go to a three-phase grinder and use a variable speed drive primarily as a phase converter. You can take advantage of the variable speed if you want, but basically a good, healthy variable speed drive will give you three-phase output from single-phase input. Now, I'm going to, from here on, you mention specific pumps that a local distributor has, mostly because I have used them. I am used to them. If you want another pump with similar characteristics, go right ahead. I'm just saying as a guideline. The Zoller 295 has a two-pole motor speed, typical of a lot of recessed impellers, 3,600 RPM less whatever slippage. Recessed impeller, and they are rated to handle 2-inch solids. Being recessed, they're quite happy at 3,600 RPM and close. And thanks to minimum overhang, you don't have any issues with shaft breakage, and they're quite clog resistant and fairly quiet. Okay, and like so many of these, they are available with a guide rail system permitting full lift out capability. You can work to service the pump. You can slide it up the rails and has an automatic disconnect arrangement. Okay. While effectively a large domestic pump with single mechanical seal, the 295 Zoller is quite suitable for light municipal applications, operating virtually anywhere within its broad head and capacity range. For this reason, it's a good choice for pressure systems where the system head can vary wildly. Its high flow capabilities provide good line scouring when static head is low. The fact that it runs out safely means that in those applications where there's low friction, there are not too many pumps operating, that high flow will act as a bit of a scouring to pick up and discharge any solids that are floating around. Did have an application where we used a number of these in a pressure sewer system, a collection of warehouses, and each one got a pump station with a couple of these pumps in it, and it worked very well. Moving up in recessed, the Myers 3RH has, again, a 3,600 RPM less slip speed, recessed impeller, again capable of handling 2-inch solids. With the recessed impeller, again suitable for high-speed operation, very clog resistant. While the 3RH is relatively small in size, it is a full municipal pump with tandem mechanical seals, ideal for higher head, lower flow rate applications. Due to the limited horsepower ratings and propensity of recessed impeller pump to increase head fails, the operation of the rate of the curve should be treated with care. Make sure you got the horsepower. And here you can see it is also available as a slide rail. It's like a mini scaled down regular sewage pump, but sort of boxes out of its class. You can, nice little station with 3-inch 80 millimeter pumps and valves and piping. Makes it sort of, as I say, sort of a 3/4 scale station. And as you can see here, you notice on the curves how the horsepower goes up, like full trim 5 1/4. As you run out, you pass through 5 horse, you pass through 7.5 horse, and you're well into service factor as you go. You've got to have the horsepower if there's any possibility. What I would do is take a look at what static is, because you obviously are not going to go below static, and make sure you can live with that at full run out. By the way, the little dotted line is really saying that we don't want to go too far out, primarily because of horsepower issues. Now, 2-horse grinder. Myers makes a 2-horse grinder, which is, the motor in that is very similar to what's used in the recessed impeller pump. And the big thing is, say, they have relatively steep curves and everything else, but they have to grind it. So developed originally for domestic pressure systems. Pardon me, I was talking about the motor. It's the next size up, the 7.5 horse. But anyway, This thing is a 2 horse, and it was designed for domestic pressure systems. Pressure systems meaning you have a number of small pump stations pumping into a common header, and they turn themselves on and off. Now, if you operate any grinder pump at high volume, the, the higher the volume the pump is pumping, which meaning lower head, the less chance there is to cut any particular volume of solid sewage with solids in it. Okay? And again, with single phase powers available, you got problems. So again, the idea of using an adjustable speed drive as a phase converter, I think, is a far better way, and go with the 3-phase pump. And as I say, now here's where that same motor is used, is on the Vortex. They have a 75 grinder, which is 7.5 horse, same motor as the 3RH. And there's your curves. And again, same deal. The further off to the right, the more likelihood of clogging. Excuse me. They even have up to a 15-horse grinder pump. And same comment. You can see in the cutaway, by the way, that their Myers grinders actually use a Vortex impeller, very low capacity, very low capacity, high head, 3,600 RPM impeller there. And you can see the grinder below that is actually shredding. Looks like a carburetor in a house. It's actually shredding peripherally any solids that are involved. And again, you can get them with guide rails for lift out. There is a manufacturer out there that uses a progressive cavity type pump, and in spite of their claims, which have gone on for years, they are not very good, dare I say, to the point that a number of people, including Myers, actually offer a version of their recessed impeller grinder pump that will interchange with the progressive cavity type pump. Now, here is sort of a small pump option curve. If your heads are down in the range, what are we talking here? Say 60 foot and below sort of thing. And those capacities are good, which really pretty much define it, say 200 gallon a minute. The Zoller 95 is just fine. If you're looking for higher capacities, higher heads, and want to use a recessed, then the Myers 3RH is the way to go. At even higher heads, or if you want to chance it at the lower flows, is their 2-horse grinder. Above that, the 7.5 horse grinder. And above that, the 15-horse grinder. So you can kind of look at that and make your decision as to what you go with. When you larger pump recommendations, there are several variations of solid handling pump. Submersible. They have several advantages, including minimal above grade structure, ideal inlet flow, assuming no wet well swirling actions, and full removability for servicing. Okay, no real limitations on the submersible pump sizes. You can get some huge units, but larger units do require appropriate lifting, etc. I mentioned earlier about the station on Vancouver Island that had a 150 horse and a couple of 250 horse. That's a 250 horse with somebody standing alongside. And I mentioned about vortexes being created and then getting a ground. There's actually the vortex. That's with one of the pumps, adjacent pump running 250 horse, and you can see the vortex that's forming there, that circle. Okay, fine. Dry pit. If you're going into a dry pit, appreciate if you use submersibles as the pump within a dry chamber, they're essentially flood proof. Okay? And very often that approach is taking, if you're retrofitting an existing station. For example, I remember one that had shaft drive from above, and it was quite deep, like 30 feet, with intermediate bearings on the shaft, and also was replaced with 3, and I got a picture of it later on, with 3 150 horse, I believe they were, submersibles. Most submersibles can be used in a dry pit configuration like is shown here. Pump cooling, usually not an issue. Now, if you go to the classic, back in the day, dry pit, dry motor was the way things were done. Um, Horizontal, you get them horizontal, as you see here, with a spacer coupling, of course, if you want to service it. You don't see that too often. Classically, the way it's done is with a pedestal mount like this, shown to the right, um, and a motor, either P-base motor, which is a low thrust vertical motor, or a C-base, which is actually a horizontal motor that can be mounted vertically. And impeller axis, fairly simple. The GVS and DD or Metro Vancouver, what they would do is attach the motor stand to the pump frame, so they could actually, once the motor was off, which wasn't too hard, simply catch it at the top of there, lift the whole damn thing and pull out the impeller. Now, also you could get close coupled units, again where the motor had a custom shaft for the seal and everything else. Very compact, very easy impeller access, but there's limitations as to how large you can go with the thing. I think, if I recall, 8-inch at about 75 horse is the limit. If you've got deep wet wells, like I mentioned, in the day, not uncommon to go with long shaft driven. These long shafts, and you could see this one actually has steady bearings at elevation 1, elevation 2. Depends how long the thing is. And basically what these shafts are light car drive shafts. In fact, they're made by a company that makes them for cars and trucks. If you do that, you want to guard at the bottom because if a joint should let go, whatever, that shaft can cock and go around. I heard that somebody was actually killed once with one of those. Shaft let go, flying around and killed them. And comment being, by the way, the joint at each joint, the shaft should not be dead parallel, dead straight in line. You want a slight misalignment, about a 1.5 to 3 degrees, to avoid either fretting or derailing. You want the shafts parallel, the initial shaft and the final shaft, but anything in between, you do the pump shaft and the motor shaft, but in between the drive shafts themselves angled a little bit, and that slight angle allows the roller bearings to actually do something, so you don't get fretting involved. And as I say, if they can get big, when you get beyond a certain point, roughly 20-inch, you can see where the pump doesn't have an elbow. It actually is designed to mount right on the foundation with a bottom inlet, and the design of the station will incorporate the elbow. Okay. Now let's look at pictures. This is a fairly new, actually a rebuild of a new station replacing an old one. And you can see these are shaft-driven pumps. And if you look at this thing, 23.5 meter head, 2170 liter per second, maximum RPM 435, so low. And I can't remember what the horsepower of these things are. But anyway, Ibera is out of Japan and specializes in making very large pumps. Two-stage. We talked before briefly with end suction pumps or any pump really, about running two-stage, the discharge of one pump into another. And it is possible to combine a pair of wastewater pumps in series to at it had essentially double. Okay. It's simplest if the two pumps have identical performance curves, but you can go non-identical if you know what you're doing and are very careful. Control system for these must ensure that if one pump is shut down, the other will also be shut down. It is permissible to start the first stage pump slightly before the second, so you get sort of a stagger effect. Doing it that way, the first stage pump will provide pressure to the second stage pump, and again, when you're shutting down, shut down the second one, and then after a slight delay, the first one. And ideally, both pumps, the motors will be powered off a single overcurrent device. We'll get into electrical later, motor circuit protector. That way, if it trips, it takes down both pumps. Now, war story. Back in the mid-70s, GVS and DD, Greater Vancouver Sewerage and Drainage District, now Metro Vancouver, wanted pumps capable of 2,000 gallon a minute at 320 foot head. So what we did was offer 2 pairs of pumps. They wanted to have duplicates. So we actually had a total of 4 pumps, and each pair had a vertical shaft-driven first stage pump, quite low, with long shaft, feeding up to a vertical coupled motor-driven second stage pump that was on the control floor. And explain here, okay. All pumps were 6 by 6 by 17, which means 6-inch by 6-inch by maximum 17-inch impeller. Although operating at 1,800 RPM less slip, they in actual fact were 15 was maximum you could use, and driven by P-base 125 horse 1,800 RPM motors. Each pump had a ductile iron casing, ductile iron, not gray iron, cast with a modified pattern that increased the wall thickness from 5/8 to 3/4. That was important for the second stage because they were the ones that literally double the normal pressure, but in fact they used them on all of them simply to standardize. And they had ribs cast on the outside of them, much like you saw with those Ibarra pumps, to reinforce them. These pumps are still in use today, and the actual field total dynamic hit is 286 feet, or 143 feet per pump, which means they operate with slightly better efficiency than originally anticipated. Let's take a look. You can double, like a vertical turbine, you can double the values on the left-hand side. Like originally, they were around 160 foot or 320 total. As they say, now the head is not quite as high as they had estimated. So we're what you say 144 or whatever, something like that. Double that, 290 something. There is the curves of those pumps. For wastewater, here's a bit of a guideline, again, like we did with water, as to how you should go and what you should use for control or can use for control. Like open discharge, where you're, manhole pumping to God knows where, not a pressure system. The different options, across the line or soft start, if you got low friction, if you're variable speed, if you have high friction, and we'll get into, start the concept right off the bat. Variable speed is not the be all and end all. And I've seen recently people claiming, well, variable speed, you're going to save energy. There are applications where using variable speed distinctly will waste energy, be less efficient than constant speed, okay? We'll get into that later. Water application, conventional wastewater pump, basically high specific speed units, high flow rates, and they can be used for drainage or for low-ed water supply applications. Here we have a lake, and the water supply, actually, they're almost like swimming floats out there, but they have submersible, what would be sewage pumps on little guide rails because they don't need to go deep, and pumping through a floating line to shore. And they don't know the difference that they're not sewage pumps. Okay, so that separates that, and I hope you have enjoyed.